The question is, in figure, let the regions z greater than 0 less than 0.3 meter and z greater than 0.7 and less than 1 meter be conducting slabs, which carries a uniform current density of 10 ampere per meter square in opposite direction, which is shown in figure. We have to determine the magnetic field intensity H vector at different value of Z. So here there are two conducting slabs, upper and lower. In upper slab, conducting slab, there is a current density and it is in positive y direction. While the lower conducting slab having a current density of 10 ampere per meter square and its direction is towards negative direction of unit vector y. So from here we have to determine the magnetic field intensity H vector, and since this is an infinite conducting slabs, so the current distribution is symmetrical, so we can apply the Ampere circuital law. So from here we first consider the upper conducting slab. In the upper conducting slab, the current density is towards positive y direction. So from here we take a upper conducting slab and we consider a direction of unit vector y is pointed out. So by using a right hand thumb rule, we can observe an Amperian path and its direction is anti-clockwise because the direction of current density is pointed outward, out of the page. So the curl of the finger is the direction of the Amperian path. That determines the magnetic field intensity. So here we consider the upper conducting slab in which a current density is toward positive y direction. And from the given figure, this conducting slab having a width of 0.3 meter, that is shown in figure. So we assume an Amperian path that is inside the slab or outside the slab. So here we consider a two Amperian path, one for H suffix IN, that is the magnetic field intensity inside the slab, and H out, that is the magnetic field intensity outside the slab. So here we consider an Amperian path inside and outside the conducting slab, and the direction of the Amperian path is given by the right hand thumb rule, that is a anti-clockwise direction. So from here, as the conducting slabs are of infinite dimensions, the current distribution is symmetrical, so we can see that there are an infinite number of conducting filaments. So if we assume two neighboring points in which a current is pointed out, so we get a small Amperian path, and from here we can see that the Z component of H, that is a HZ, are cancelled. We get only the X component of H. So from here we find that the vertical, that is Z component, is cancelled and we get only the H component of H. So from here we find that above the conducting plane the magnetic field intensity is towards positive direction of X, and below this conducting sheet the direction of magnetic field intensity is towards negative direction of unit vector X. So now we can apply the Ampere circuit law. Since the Z component of H is cancelled, we have only the X component of H, and we apply the Ampere circuit law. First we apply Ampere circuit law inside the slab. So here we use an Amperian path that correspond to H suffix IN, in. So from here we take a closed line integration S dot dl vector equals to current enclosed, and this current can also be determined with the help of current density, that is J into area, because we know that the formula of current density is current upon area. So the current is equals to current density J vector, or this is a magnitude, J into area. The area of this Amperian path that is the inside the slab, and its dimension here we consider that the width is W and the height is small d. So the area of this Amperian path is W into d. Now we apply the Ampere circuit law, and since the two path, that is the h component, is cancelled, so we get only the x component of h. In the above we get a positive component of h, that is along positive unit vector x, and its width is W. So it is h suffix in into W plus, and below the sheet the direction is opposite, that is toward negative direction unit vector x, so we get minus h in, and the width, that is a dl vector, that is also a negative, that is minus W. So from here we can get 2h into W, that is equals to j into WD, and here W is cancelled, we get h suffix in, that is equals to jd upon 2. So this is the magnitude part of the magnetic field intensity H vector. Similarly, we can determine the magnetic field intensity due to outer Amperian path. But in this we get the H out is equals to J into capital D upon 2. Here we take a notice that outer Amperian path encloses the width capital D of the conducting slab. So this is a point which is to be noted. Inside the slab we take a height or width small d, but when we take the outer Amperian path, that outer Amperian path encloses the conducting slabs only. So we take a width or height, that is d, capital D. So we can write the magnetic field intensity H vector for above upper conducting slab. Since the magnitude is J d upon 2, in upper surface the magnetic field intensity is towards positive direction of x, and below it is towards negative direction of x. Now we consider a lower conducting slab, and in lower conducting slab the current density of 10 ampere per meter square is flowing in towards negative y direction. Now we consider a lower conducting slab in which the current is flowing towards negative direction of unit vector y. So here we consider a J vector, that is a current density, and its direction is pointed inside the page, as the unit vector y pointed outside the page, and the current density is flowing opposite to unit vector y, that is pointed inside the page. Similarly, we use an Ampere circuit law. For this we assume an Amperian path. As the J vector is pointed inside the page, so the direction of the Amperian path is clockwise direction, and it determines the direction of magnetic field intensity H vector. Inside the conducting slab we consider a height or width, that is small d, and outside the conducting slab, that is the Amperian path outside the slab, we consider a width or height, that is capital D, because the outer Amperian path encloses the conducting slab height only, that is D, capital D. So similarly we get a H in is equals to J into small d upon 2, and H out is equals to J capital D upon 2, because in this case also the vertical component, that is the Z component of H, is cancelled, and we get only the X component of H. In this lower conducting slab we find that at the above surface the magnetic field intensity H having a direction towards negative direction of unit vector X, and below this we find that the direction of H is towards positive direction of X. So in this way we can write the magnetic field intensity H vector for the lower conducting slab, that is J into D upon 2 minus unit vector x, that is for above surface, and G.A.T.E upon 2 unit vector x, that is below the surface. So we observe the information for the upper conducting slab and lower conducting slab, and we find out that between the two conducting slab, the direction of H, that is the magnetic field intensity, is towards negative direction of x. That is the same direction, and outside it we find that the direction is towards positive direction of x. So now we start a question, that is we have to determine the magnetic field intensity H at z equals to minus 0.2. As this point z equals to minus 0.2 is below the two conducting slab, and as the current is flowing in opposite direction, so the summation of the magnetic field intensity for both the slab is 0 because the current is flowing in opposite direction. So at z equals to minus 0.2, the fields from top and bottom slab are cancelled. That is due to the flow of current in opposite direction. From this region, the magnetic field intensity at z equals to minus 0.2 is 0. Next is we have to determine the magnetic field intensity at z equals to 0.2 meter. Here the 0.2 meter is lie within the lower conducting slab, and this point is situated in lower conducting slab but above the midpoint. The midpoint of the lower conducting slab is 0.15, and from here we can determine the magnetic field intensity by using Ampere circuit law. And in this we know that in the lower conducting slab, between the slabs, the direction of H is towards negative direction of x. As the point 0.2 is near to the upper surface of the lower conducting slab, so the orientation of the magnetic field is towards negative unit vector x. Now we have to determine the d value, small d. To determine this, we find the midpoint of the lower conducting slab, that is 0.15, and the given point is 0.2. So we can say that the width or height small d is equals to twice of the difference with respect to middle point. So d is equals to twice of 0.2 minus 0.15, and we get 0.1. So in this way we can determine the height d, that is 0.1. And the magnetic field intensity H vector contributed by the lower conducting slab is J into d upon 2 minus unit vector x. Here the value of d is 0.1. But we have to determine the magnetic field intensity due to both the conducting slab. So the magnetic field intensity, that is total magnetic field intensity, that is due to the lower conducting slab plus upper conducting slab. So the lower conducting slab having a width of 0.1 while the upper conducting slab having a width of 0.3. So by using the formula we can find the total magnetic field, that is minus 2 unit vector x ampere per meter. Here the point is noted that 0.2, this point is near to the upper surface of the lower conducting slab, and we know that the magnetic field between the conducting plane or slab is towards negative direction of x. So the second term is also having a direction that is towards negative direction of x, and the answer is minus 2 unit vector x ampere per meter. Now we consider a third case, that is we have to determine magnetic field intensity at z equals to 0.4 meter. 0.4 meter is in between the two conducting slabs, and we know that between the slabs the magnetic field intensity is towards negative direction of x, and by using Ampere circuit law, by assuming the Amperian path, we find that between the conducting slab the Amperian path is added up. So we simply add the two magnetic field intensity, that is due to upper and lower conducting slab, and here the direction is toward negative direction of unit vector x. And here the impedance path for upper and lower encloses the width, that is capital D, and its value is 0.3, and the answer is -3 unit vector x ampere per meter. The next is we have to determine the magnetic field intensity H at Z equals to 0.75, and here the point, that is 0.75, is lie in the upper conducting slab, but this point is below the midpoint of the upper conducting slab. The midpoint of the upper conducting slab is 0.85 and this point is 0.75, so this is below the upper conducting midpoint, and we have to determine the value of small d, that is 0.2. Here to determine the value of d, we again using a formula, that is twice of difference with respect to midpoint. So here the midpoint is 0.85 and the point is 0.75. So we get d equals to twice of 0.85 minus 0.75, that is 0.2. So in this way we can determine the small d, that is 0.2. And the total magnetic field due to both the conducting slab is, for the upper conducting slab we use d equals to 0.2 and for the lower conducting slab we use a 0.3, and the direction of the magnetic field between these two conducting slab is towards negative direction of x. So after putting the value of J, that is 10 ampere per meter square, we get the answer, that is -2.5 unit vector x ampere per meter. And the last part, that is we have to determine the magnetic field intensity at Z equals to 1.2 meter. 1.2 meter is lie above both the slabs, so it is outside the system, and again the magnetic fields are cancelled completely because the current flowing in opposite direction, and we get a magnetic field intensity H, that is 0. So in this way we can determine the magnetic field intensity at different points by using the Ampere circuitry law, because here the current distribution is symmetrical.